lecture, we will define several characteristics of intelligent agents. Let's first think about what does it actually mean, intelligence. We will not provide an exhaustive definition. We will just, at this point, loosely characterize it, that it has several characteristics that are typically associated predominantly with humans, and that is that we can comprehend abstract concepts, that we have ability to understand mathematics, abstractions, we are capable of using and creating languages, we have a memory, and we are able to plan complex tasks. We daily make decisions based on logical reasoning, but we also, as humans, as a part of our intelligence, we have emotional intelligence, and we have either codified or implicitly understood certain moral principles. How does this relate to artificial intelligence? So artificial intelligence can be considered as intelligence associated with machines from several perspectives. One perspective, which is kind of implicit, is to think about a so-called a test which will not define what is intelligence, artificial intelligence, but it will define that if a machine is able to act indistinguishable from human, which while human is intelligent, then the machine itself will be considered as an intelligent system. Such a test has been defined by Alan Turing in 1950. And the computer or machine passes the intelligence test if humans cannot determine whether the responses come from a person or a computer. So we will obviously have some kind of interface which the human will be receiving. In the case of Alan Turing's considerations, this would be rather of a textual outcome rather than a natural voice. But in today's considerations, we can think of a system where you are, as a human, performing conversation with another entity, and on the other end, the entity is responding also with natural voice, and we as humans would be or not be able to distinguish whether on the other end of the channel there is a human or a computer. So from this definition, which is an implicitly defining intelligence, we have certain requirements that as the input will be from the human a natural language, then the computer will be necessarily need to be able to process the natural language and represent that input in some kind of knowledge representation that will be subject of certain reasoning process and learning, and then also again a natural language processing, in the sense that it will be, the outcome will be synthesized into a natural language output, which would not only be reading naturally, but also perhaps sounding as a human voice. There is also something called total Turing test, which includes even an interaction with objects and people, and that would require additional perceptual inputs such as computer vision for sensing mechanisms, vision-based sensing mechanisms, and robotics, meaning some actuators like certain limbs, artificial limbs, which will be able to perform certain actions. Another way how we can define artificial intelligence to think about like how we will define human intelligence, and then we will relate it more explicitly to the artificial intelligence. And human intelligence is studied by cognitive sciences, which are typically interdisciplinary scientific disciplines, ranging between psychology, neuroscience, and also computer science for that matter. They would develop computational models and testable theories of the processing within the human mind, meaning the neural processing in the brain and in the neural overall system. These studies can be based on, for example, introspection. This means that the subject whose neural processing is being studied, himself or herself is thinking aloud and studying it themselves, so to say. That is one approach. Another approach is that there are so-called psychological experiments or psychophysical experiments, which would be typically based on either typically non-invasive, based on some stimuli. The subject will respond with a certain response, and this response will characterize the human neural processing and also perceptual processing for that matter in case of some visual stimuli. And then we have various ways of study the brain in terms of imaging. So we would have electroencephalogram imaging, or we could use various other imaging modalities, such as, for example, functional MRI, which measures the consumption of glucose within the brain, which is associated with the processing centers of the brain for a given task. So there could be some kind of a stimulus which is specific, and based on the stimulus there will be a certain part of the brain which will be processing it, and that could be studied by the so-called functional MRI imaging. So, and on top of that, these days neuroscience will be deploying AI in the analysis of this imaging data with the aim to somehow read the minds or read what the person is thinking about, which is to some degree already starting at this point, and we can expect that this will be more and more well developed in the future. The third aspect, how we can characterize artificial intelligence, is not to think directly about the human and their processing and associating intelligence to humans, and if the machine is performing like a human, then it will be also either explicitly or implicitly considered as intelligent. But instead we can define something which is called rationality, and if a machine is thinking rationally, then it will be an intelligent machine. Rationality is a sort of a reasoning process. There are various aspects of it, but the reasoning process has been defined in the field of logic, which is either associated with the field of mathematics or computer science, where we can think of some simple basic logic, like considering statements like Socrates is a man, and as all men are mortal, this implies that Socrates is also mortal. So this is a basic logic which has certain implications and logical operators. The logic is typically dealing with information which is certain, where we have binary information. Something is either true or something is false. And that is sometimes sufficient, but most of the time we are dealing with a certain uncertainty. we are not completely sure about a certain state, if you like, and therefore much more powerful systems are employing the so-called probability theory and statistics, and also a field of fuzzy logic that allow reasoning even with cases when the information is uncertain. So this is a working definition where which we will be using throughout of our lectures, where we will be associating the intelligence of machines with the rationality. On the top of that, of the rational thinking, we can associate intelligent machines with an output in terms of their rational behavior, that they are acting rationally. So, and for that, again, we can consider the thinking part as a certain computational capability, a certain learning capability, certain knowledge representation, and on top of that, we need, if the machines are supposed to relate to a certain environment, they need to have a certain perception mechanisms, some sensors, and also they need to perform certain actions which are typically exercised by certain actuators, or even just certain outcome, like a speaker, for example, in terms of natural language. Now, but in this case, in rationality, we are not focusing on modeling human behavior. We are focusing, loosely speaking, on doing the right thing given a certain output. And this can be realized through certain various functions, and this has been developed in various branches of sciences, maybe through in mathematics or statistics, through the so-called cost function, or through loss function in machine learning, or in reward or utility functions, which would be typical names also occurring in fields like economics or operations research. So these functions can be either minimized or maximized, and with that we will be measuring how much the machine is doing a certain thing right. However, this approach has a certain limitation, because given a certain cost or loss, there could be not only the solutions which are intended to be the right approach to solve a certain problem, but there might be a lot of other solutions which we might not think about. Like, for example, imagine that we have a chess game, and the machine is capable of controlling various aspects, maybe even the voltage of or access to supercomputer. Maybe the machine, in order to win a certain chess game, or maybe a more complex game, would maybe allocate its computational resources for its task of solving the chess problem at the cost of some other computational demands or tasks, which are perhaps even more important. And the machine will simply maybe reach its goal, but at the cost of some other aspects being heavily compromised. Or maybe it will simply decide to win it by cheating, or maybe it can decide to not to lose by simply just lifting the chessboard and throwing the individual players' figures away from the chessboard. So we need to understand that there might be the so-called value alignment problem. So this is a standard model. Acting rationally is a standard model of artificial intelligence, but it might suffer from this value alignment problem, where the value as the humans expected is different from what the actual cost function is driving the machine to perform. So the ultimate model of artificial intelligence needs to also integrate something which is related to benefit. So it needs to be provably beneficial to the human and not having undesired, not beneficial ways of solving the problem. So we can consider as the rational agent through these various aspects, like for example we said that if it should be acting rationally, it should have a certain percepts which are sensed by its sensors. It should have a certain knowledge representation and computational power, and then it should have certain actuators which are acting upon the environment and are performing certain action. So we have an environment in which this agent is performing its task. So there is an input through percepts, there is some processing, and then there is some output, and that's typically how intelligent artificial agents will operate. The perception using a sensor might be or might not be stored in entire percept sequence. This means that we will not only have the perception of the current state, but also store the past percepts from the environment that will be useful for completing the task. The so-called agent function is implemented as an agent program that maps the percept into a sequence of actions. Look at this example. We will have a very simple agent, which will be a robot, which will be a vacuum cleaning robot, and it will have just the job of cleaning two tiles, the tile A and tile B. And there will be relatively simple operations which the robot can do. It can do movement, so it can go left and right, and then it can sense whether something is dirty or something is clean, and then it can also perform an action of sucking, which means that it will be vacuum cleaning and cleaning the respective tile. So we can, for example, have the following percept sequence. We can have the state where the robot is in the tile A and the tile is clean. And the corresponding action for that moment, if it's tabulated, should be that it's going to the right side. And there it should investigate whether it needs to do some cleaning or not. If the A and tile is the position of the robot, but it's dirty, the tile, then the necessary action in order to perform its tasks is to clean it. So the suck will be the action which the robot should do. In case we have a percept sequence where the percept is B, being in the tile B, and the tile is clean, so then the necessary action is to move to the left. If we have B and position and the tile B is dirty, as sensed by the robot, necessary action is to suck the dirt. So, and then we have a state where the A is clean and the A is clean. So then the action should be to go to the right side. And we can have a percept sequence A is clean and then A is dirty because it got dirty. Then the necessary action should be to suck, and so on. And we can have basically an entire sequence of percepts which this robot might have over its lifetime. defining for a robot to have a certain measure of its performance. How good is the robot performing? Like, for example, having the defining the goal as the work done might lead to some outcome, maybe also sometimes to undesired consequences. Imagine that we measure for our vacuum robot that it's measuring the amount of the dirt it sucked, and we want to maximize the amount of dirt which has been sucked by the robot. Well, in such a case, if we will have a utility function, or actually the goal which will be driving the robot to maximize this, then the robot might as well dump the dirt and suck it again and again and again, and with that maximize the amount of dirt which it was cleaning. And clearly this would be undesired behavior. So the goals need to be typically aligned with the goals of human, and it should be rewarding the goals, such as, for example, the clean floor rather than the volume of the sucked dirt. So, but there are also other aspects of our performance measure. For example, how fast this should be done, how much energy should be spent, how long the trajectory should be, and other aspects, because it might be that the robot, instead of cleaning dirty tiles, will be just going from left to right, and only occasionally will be sucking the dirt, and this is clearly not an ideal behavior. So the performance measure can be a more complex characterization of the desired performance of the intelligent agent. Or we define the several aspects of rationality in our intelligent agents formalism, and all these are necessary to be considered. So first we have the performance measure, which we have been talking about, and for example, it's a criterion of success. In case of our robot, it could be awarding points for each clean square over its lifetime of 1,000 steps. So we have a limited amount of steps, and if we want to maximize the amount of clean squares, then certainly a part of the actions need to be related to sucking and not only moving. Then the second aspect of rationality is to have certain prior knowledge about the environment. So the space, for example, of the environment could be known, but not everything about the environment is known. For example, the initial location is not known of the agent, and it's also not known what is the distribution of dirt. But we know that in this environment, if the tiles are cleaned, then they will be remain clean, and that the sucking will clean tiles. So this is kind of the limited environment which we are assuming in this example. And then, for example, we have the agent's actions and abilities, like, for example, move left, move right, and suck. And then we have the agent's percept, and that is the sequence, which is the perception of the location and the rationality. In terms of our rational agent, is something which is the expected performance or expected world. It's not necessarily the actual world or the actual performance. So actual knowledge of the environment or the outcome would be called the omniscience, and the actual performance, which is maximized, will be the perfection. But rationality is not maximizing the actual performance, that it is maximizing the expected performance. So rationality is not omniscience, and it is not perfection. The agent will typically include some, if it doesn't know enough about the environment, it will also include some actions to collect a certain information about the environment, and this is using its perception, and this is called information gathering for learning the environment. So the rationality is about perception, exploration, learning, and autonomy. And therefore, this task environment we characterize in the so-called PEAS characterization, where the P stands for performance measure, E stands for environment, A stands for action, and S stands for sensing. So the task environment are describing the problems for which the action is a solution. So for example, if we have an autonomous taxi, we have the performance measure to drive safely, drive fast, drive legally, comfortably, drive profitable as a taxi, have a low impact on other participants on the traffic. The environment is the road, is the actual traffic, so other cars, police, pedestrians, the customers, or the weather. And the actions could be steering, acceleration, braking, signaling, horn, or display, or speech to the customer. Sensing, typically autonomous taxi will have some computer vision, realized through cameras, radar, laser, like LiDAR, and speedometer, GPS coordinates, engine sensors, and so on. So this would be the characterization of an autonomous taxi type of intelligent agent. So, and we can look at this task environment from various aspects and characterize it from those. For example, observability. We can have an environment which is fully observable. Like, for example, if we have an chess system, we can observe the entire world of playing the chess, the entire 8x8 tiles on which the chess figures will be placed. Or we can have an environment which is partially observable. That means that we only partially know about the environment's characteristics. And if sensors give access to complete state of the environment at any point, then this means that it is fully observable. This is this then leads to that we have the complete information about the environment and all the aspects, and we can completely certainly choose a certain action. We do not, in such a case, when we have a complete observability, we do not need an internal state to keep track of the world, because we know everything about the world, and this is, however, not available in most cases of scenarios, and it's partially observable, even just because there is a noise in the sensing, and the sensors are, for example, inaccurate. So, but typically imagine that we have a partially observable environment with a robot being able to sense with its cameras, but the cameras have a certain field of view, and obviously the entire environment cannot be sensed by that. There are some, if there are no sensors present, we can also say that the environment is unobservable. Then another aspect to consider our task environment is to look at whether we have a single agent or we have a multi-agent system. Where the single agent, you can imagine that if you have a crossword puzzle type of intelligent agent system, then this crossword puzzle will be just a single agent. and solving the crossword. However, in case of traffic, we might consider the other cars as a part of the environment, or perhaps they are also autonomous and maybe they are also agents themselves, and in such a case we will be dealing with an multi-agent system. So it's a question whether to characterize an object as a part of the environment or whether it is an agent. And typically we can say that it depends on whether the performance of B, agent or object, is affecting the performance of A. So we can have, for example, competitive multi-agent environments, like for example chess, where minimizing performance of B will be maximizing the B's performance leads to minimizing of performance of A. But we can also have collaborative or cooperative multi-agent environment where the agents are jointly maximizing their performance. So, for example, if there is an for obeying the rules principle in the traffic, generally we can say that these agents are cooperative and they are because the overall traffic will be more smooth. And in such a case, in a multi-agent environment, this is not necessarily always the case, but there could be an explicit communication between the agents in such a multi-agent environment. Then we can talk about the task environment in and analyze the aspect of determinism. So is this a deterministic environment, or it is a non-deterministic or stochastic environment? So if the next state of the environment is completely determined by the current state and the actions of the agent, the environment is deterministic. So if we do a certain action, we can be 100% sure that the state of the environment will change from one state to another, or will remain in the same state, for that matter. We do not really. The task environment can be also characterized according whether the tasks are somehow arranged in a sequence, where one possible action somehow influences the next step. So, for example, if we have image classification and we have 1,000 images and one image has been classified, whether it contains a cat or not, it doesn't, when the next image comes, it doesn't really affect the outcome of the next classification task. And in such a case, we are talking about the episodic environment, where the agent's experience can be divided into atomic episodes, and one episode doesn't depend on the previous episodes. If the action in each episode only depends on the episode itself. In the sequential environments, the current action affects the future states, and it could be also in kind of a short term or even can have long-term consequences. Then we have the so-called static or dynamic environments. If the environment is static, the environment itself doesn't change without the agent's action. And even if the agent changes the state of the environment, in our classification, the environment is still considered as static. So from that definition, the chess playing game will be a two-agent system, which is in fact static, because if the agent doesn't do anything, the environment will not change. So if the environment cannot change while the agent is thinking, the environment will be static. And in such a case, we do not need to sense the world while the agent is thinking, because we know that there is not change in the state. In case of a dynamic environment, there will be changing irrespective of whether an agent is performing an action or not. And therefore, if the agent is still processing, it also, if it's not performing any action, it's actually in such an environment, we need to characterize it as that the action is doing nothing while the agent doesn't act on the environment. There could be also something like semi-dynamic environments where the environment does change, but the performance of the agent is somehow associated with the duration. How long did the agent take to solve a particular problem? So, for example, if our chess example will be equipped with clock, and the agent, it takes a long time to think about the next step, then it will be semi-dynamic environment where the longer the agent is thinking, the less performant the agent will be. Then we can characterize the environment and in terms of how continuous it is. Or how discrete it is. So, for example, we can have discrete environment in terms of space, but we could have continuous time, or we have a discrete space and also discrete time, and also discrete percepts. So the discrete versus continuous can be applied to the state, to the way to the space, to the way the time is handled, and to the percepts and actions of the agent. And the environments can be mixed in the way that the taxi driving has a continuous state, time, and actions, but it has a discrete percepts, because the frames of a digital camera, which it is equipped with as a sensing mechanism, are delivering images at a certain discrete time steps. We have a characteristic of a task environment in terms of familiarity. And this is not really about the environment. The environment can be completely fully observable, but even if it's observable, maybe the agent doesn't really know the meaning of that environment. So it is unknown to the agent. Even maybe the task can be unknown to the agent. So it characterizes the agent's state of knowledge about the laws in the environment. And even in the fully observable case, the agent might not know how does this environment work. So, for example, imagine that an agent will be subject of winning a certain computer game, and it can fully observe the computer game, but as it doesn't know the rules of the game, it will be at the beginning an unknown environment for the intelligence system, because it will not know the rules of the game. We can have here several interesting examples, like, for example, Sudoku, which is a typical game for to solve a puzzle, and it is deterministic. It is sequential, so because one solution depends on how the next solution will then look like. It is static. It doesn't change if the agent doesn't make its steps. It's discrete. Because we discretely solve entering the numbers into the corresponding cells. And it is a single agent, because we have the environment, the Sudoku itself, and then we have the agent which is solving this Sudoku. We can look at the poker, which is partially observable, because we can know the cards of ours, but we don't know them in the deck or in the opponent's hands. And then it is stochastic, because it's also multi-agent environment. It is sequential, so the one step, one draw is affecting the future. It is static and discrete. We can consider also as a task environment, for example, the internet shopping, which is partially observable. We don't know everything. It is stochastic, So it is not predetermined what will be purchased at the before the actual steps, so to say. It is episodic. Purchasing one element doesn't necessarily influence what will be the next purchase item. It is dynamic, so some goods could be added or removed during the action itself. For example, it's discrete, and then it is also multi-agent because we have several shopping agents performing at the same time. And taxi driving is also partially observable through the sensors. It is stochastic because there are other agents contributing to the environment. And then we have it's sequential because one turn, for example, in the street affects in which streets we will be. It is dynamic from the perspective of the time and space and maybe actions. It is continuous, and it is the multi-agent environment. So here are several examples characterized by the properties of the task environment we have been just talking about now.
Now that we have discussed several types of examples of environments where intelligent agents can be used, let's have a look at what is the structure of an intelligent agent. And we will discuss various degrees of their intelligence. Um, so agent in principle is composed of a certain architecture and a program where the architecture characterizes its basically hardware capabilities in terms of its computing device or the sensors it has or the actuators upon which if it acts on the environment. The program is basically the software which the agent has, which has to be appropriate to the architecture. So it should not have features which the architecture doesn't allow, or at the same time, it should properly characterize the, or utilize the architecture the agent is capable. So the program takes the current preset as input from the sensors and then returns an action to the actuators. And in between, the program can be of various degrees of complexity. So the simplest agent we can think of, this is not really practical, but from theoretical perspective, we can think of a so-called table-driven agent, where the percent is added to the percent sequence or it is stored, and then we identify a row of at the table where this would be a table of basically consisting of two columns. So on the left column there will be a percent sequence, and on the right column will be the corresponding action which should be taken. And you can imagine in chess that you would have a percent sequence of the entire game until the current point, and then the on the right hand side there will be the um, the next action which will be performed. However, this is unrealistic because it requires extremely high memory requirements, and it's not really intelligent. Everything is in principle memorized. This is it will lead to, in principle, reason correct outcome, maybe not reasonable outcome because everything is memorized, and we will be looking more for agents which are capable of certain smaller program which is able to perform similarly well without taking such a high demands on the memory. So the simplest agent program will be a simple reflex agent, which is shown here in this picture, and we can see that it is the agent is equipped with certain sensors which are used to sense the environment. And then we have the characterization only of what is going on now. So the current percept is here not stored really in some percept memory, but it's just the current percept. And based on this percept, the agent is having certain rules what to do when a certain percept comes. And then based on that, the actuators will be used to act upon the environment. So it is this is not very intelligent. It's very simple. It just in principle takes into account the current situation and doesn't know anything about the history. In this way, humans also act to some degree. Imagine that if you are suddenly touching a very hot plate, um, your sensing will be connected to some basic reflex, which will move the hand away. So this could be also part of an intelligent agent to get a bit more sophisticated program, but this simple reflex allows you to perform certain actions but not with any reasoning. The next model will be the model-based agent, which is has a much more complicated internal structure, as you can see here, because it has a certain characterization of a state in which the world is in. So it has a characterization of the world and it has its internal state about work which is updated with each percept and action which is performed. So it uh, with its internal state, it keeps track of the world which is currently not perceived. So even if its camera do not see a certain aspect of the environment, it still can be utilize that information which it perceived before, because we have the perception sequence, the percept history, which is forming this state of the world. So we have a model of of the of the world, and this is characterized by the state graph in which this world and the agent are in. And then we have the transition model, which describes how the world works. Basically, when we basically we know what actions will be uh, performed given a certain sensing. So this transition model, for example, will give us the information what happens when the steering wheel is turned, that the car will be turned in case the car will be the intelligent engine will be turned. Or we can have another transition model aspect, like for example, a model of certain sensing unit, like the sensor model, will have the knowledge of changes of the sensor from the environment, like for example, if we have cameras and it's raining, that this sensor and the cameras might get wet. So this is a much more sophisticated model that allows us to uh, keep the track of the world which is captured in the set of states and which are forming a certain state machine or state graph. Then, even if we have this state graph, we do not really have information about the particular desires or goals when what the intelligent agent should achieve. Therefore, we are combining uh, uh, the model-based agent with and or equipping it with a certain set of goals. So it's a goal-based agent that describes the situation that is desirable. And this is characterized by something that the agent should achieve. So you can see here that there are certain goals which the agent should be achieving, and the um, uh, these goals can therefore require a certain more complex actions, like for example search or planning procedures. Finally, we have the most complex um, model of an intelligent agent, which is a utility-based model agent, where the agent is equipped with a certain utility function, which is much more detailed information about what is good for the agent in its role. So this means that even in states which are not fully achieving the goal, we are already can talk about a certain reward or penalty, which will be then influencing our our agent, and this agent will be then choosing between various actions to change to states which where the utility function will lead to a high reward. Local is a very clear distinction between what happy and unhappy. Now, the utility function is basically an internalization of the performance measure. So it is not just happy or unhappy, but it's a characterization towards achieving a certain goal. And therefore, we can use some uh, general tool set which could be used to maximize the agent's expected utility. In case our goals are, for example, conflicting, this utility function can take into account interaction among several goals and can choose actions which would be reasonable and appropriate trade-off. So we will be talking about it in the later lectures, but there are some general purpose algorithms that are used for maximizing a certain function, certain reward, and these functions can be utilized on any utility function, which or a broad spectrum of utility function, irrespective of their particular characteristics. Finally, we will be describing an agent which is able to learn from the environment. So learning allows the agent to start operating in an initially unknown environment. For this, for example, techniques such as reinforcement learning could be an excellent choice, because using those techniques, an agent is capable of learning the environment while performing certain actions already in the environment and receiving information whether what it did was good or bad. So even if it starts in an environment which is completely unknown, again, the robot doesn't know, even then it can start learning and performing badly in the beginning. But based on this input, it can make improvements in its current representation of knowledge of all aspects of knowledge. This learning agent has therefore several conceptual components. So it has this learning element, which could be some representation, which is able to learn. And then it has performance elements, which selects then the external actions, and it has a critique, which gives a feedback on the performance so that this we can characterize using this critique whether the action which has been taken was good or bad, and that will feed back to the learning which which will be gradually improving its knowledge. We need to note that there is also something which is called here a performance standard, which is basically characterization of the environment. If you like, maybe these are the rules of a chess game, which should not be changing over time. So this is something static, which the agent doesn't really know, maybe in the beginning, but it through its um, rewards or punishments, it will basically learn this performance standard. Then we have also um, one more aspect of these components, something which is called a problem generator. And this problem generator basically explores informative experiences so that our learning agent not only performs actions within the space it already learned, but also explores new scenarios which it doesn't really know much about, so that it can learn how to perform well also in this environment, and finally has a rich experience of the entire environment it is active upon. With this, we have completing our overview on intelligent agents, and in the next lecture, we will be looking at various strategies of search where we have a particular problem, we are looking for a solution, and we have a systematic approaches how to search for that solution.